Good morning everyone, this is just a quick demonstration video of how to use shell elements in Abaqus. I'll tie into what we did in tutorial 6 and 7 really on this T-beam we modeled with using plane stress analysis. What I'm going to do is model the same problem using shell elements. Remember correctly, it was basically a 10 meter long beam. Starting from the center of this left support, and then we had a 3 meter overhang from the central support, 19 kilonewton per meter load, 90 kilonewton per meter load. So I'm just going to start off with a basic Abaqus model. We'll construct a part doing 3D analysis this time, or modeling space. I'll call the part a T-beam. And we're going to do this using an extrusion of a shell. And I'm going to work in meters, so the modeling or the sketch space should be about 10 units long. Firstly, we draw the cross section. I'm just going to start at the bottom of the web here at 0, 0. And then we want to do a mid-surface model to model our shell as a mid-surface element. So we need to go upwards by a distance of 0.45 meters. And then I'm just going to go to the right for that 1/2 of the flange. So we're at x equals 0.4 and 0.45 in the y direction. I'll do the other half of the flange in a similar way, but this time in the negative x direction, and again 0.45 in the y direction. So that's basically our cross section with reference to this. So we've modeled that middle plane for the web and the flange. Just going to save that, or say it's done, and we're going to extrude this element by 10.1 meters. So we're doing 10.1 just to include that little bit of a over or extension there to model the left support. What we want to do now is the usual bits, define a material. This was a concrete material. The own weight was 2,600 kilograms per cubic meter. This is obviously quite high. We assume this is a heavily reinforced beam, that's why it's so high, but I mean, be any value. The elastic properties, 30 gigapascal elastic modulus, and a Poisson's ratio of 0.2. Sorry, it should obviously be gigapascals. Right, so that's it for material. And then what we want to do is define some sections. Now, this is basically the step where we define the thickness of our mid-surface shell element. And we're going to have two sections, the one for the flange. And we're doing a shell, a homogeneous shell element. Right, so basically, you don't have to change anything in this default settings except the value of the thickness, which is 0.1 meters in this case. Like I've explained in class, there's a lot of things you can do in terms of integrating the section properties, etc. But the default settings work fine. We've already defined the concrete material, so it chooses that as a default value. We want to define another section for the web because it's a bit thicker. Shell, same thing again, but we're going to do 0.2. Next up, we assign these sections to the different portions of our part. So a section assignment, we'll start with the web. I'll create a set for the web if we want to use it later on. And we just choose that as the web section, and it'll take the thickness from the assignment of the section. And remember, we're using a middle surface. In some instances, you might want to use something else in terms of the location of the surface profile, but we've given the dimensions as the middle dimension, so we'll use a middle surface. Next up, do the flange, just call this, let's make a set for the flange, say done, choose that, and say OK. So there we've assigned our sections. What remains to be done is to partition this model so that we can include our supports at the right locations. So what I'm going to do is just show you a different way that you might want to do this. There's various ways to do it, but I'm going to use this feature where we create a datum plane and we use that datum plane in this partition tool. We have to partition the face using the datum plane. So first we create the datum plane. It asks us the principal plane from which to offset. So remember, our coordinate system starts here at 0, 0 on, I think on this side, to be totally honest. It's on that side of the beam. So you'll see what happens now when we create the first datum plane. So let's just, to demonstrate where it sits, create the datum plane on at 0, 0, but it's parallel to the XY plane. Let's make it at 0, 0. So you see there it puts it at 0, 0. To see a side view of the beam, we want to go Y, Z, Y pointing upwards. So we might change our view to something like that. And let's just put the perspective on, we'll switch it off so we can see our first datum plane is at the end of the beam. So obviously to create one 200 moles to the right, we do the same thing again. We select here the principal plane again, the XY plane, but we're going to go 0.2 to the right. And then obviously we also want one at for our central, or at least from this point we're going to go 7.2 meters to the right end of that support. So XY plane again, 7.2 meters. And 7 meters. Right, that's it. But now we're going to partition this face by using our partition tool, and it asks for the faces. So select the first face with that datum plane and we create a partition. So I go back to this view, you'll see that it's made the partition there at this end of the beam now. Right, so there it sits. I'm going to do the same thing again. Select this face to partition, that datum plane, create a partition, next one. There we are. So we can just check that our overhang is correct. This should be 2.9 meters from there. If we query the distance, you can pick a node there, and a node at the end, and it tells us that the distance is actually 0. Wonder why that is. At least it shows us the correct point. Oh, I seem to have picked the 2 points on the same spot, so let's try that again. .9 meters, as expected. Just cancel that tool. This is just to show that you can actually use this query tool to get some interesting information if you want to check your model. So we've assigned sections, we've created our partitions for the boundary conditions, and now we want to mesh this model. So this is obviously an important step. Typically, you first want to assign the element, so the whole model is going to be made of the same element, but we could have had different elements in the flange or the web if there was some particular reason for it. If I go into this dialog box, firstly we'll see that automatically the shell family is switched on. We want to use linear reduced integration for node doubly curved thin or thick shell elements. This default setting, this S4R, is basically what we want to use. It's a good general purpose element. So in a schematization or a test or exam, please write down that this is what you're using, S4R shell element, so that it's clear what element you actually put in the model. Next up, we're going to assign mesh controls. We want quadrilateral elements everywhere. So again, we're going to select the whole region, and we're just going to pick quad elements. And then we'll assign some global seeds. Now this value seems a bit coarse to me. Basically, it's got only one element over the depth of the web. So I'm going to go for about 10 times smaller, or at least that would be 0.1 meters. Let's go for 0.0550 mil element sizes. Right, there we have it. And then we can mesh. And it meshes the part quite nicely. Next up, we want to create an instance of a part. That's easy. We want to create a load step. We call it load, or whatever you want to call it. Static general, accept the defaults. Just remember that for the shell element section forces, we need to go to field output and actually ask Abaqus to give us those SF section forces and moments at the output step. We're not going to switch on any history output. Only thing that remains is our boundary conditions and loads. So before I define that, I just want to point out something in terms of Abaqus's use of coordinate systems to give us output on shell element forces. I mentioned this briefly in the class, saying that if you go read the help file, you'll see that Abaqus says it chooses the shell element local axis based on the projection of the global x-axis onto the actual element. And if the x-axis is perpendicular to a surface, it'll actually default to the z-axis. Now, I want to demonstrate this by firstly defining boundary conditions in terms of the coordinate system we've got going at the moment, and then we'll redo it in a second step to show you the differences. So we're going to define boundary conditions. I'm just going to go back to my view, y pointing upwards and z to the right, and I'm going to define a displacement rotation boundary condition at both of these 200 mil long pots or lines. So done. I'm only going to constrain this model. Well, I'm going to constrain it in the displacement conditions. I'll prevent rotation of the beam in a global sense by specifying another boundary condition by supporting the one flange along its full length. So creating that boundary condition. Right, so the next boundary condition along this whole edge, we're going to just define support in the x direction to prevent rotation about the z-axis. So we'll do U1. Right, there we go. So the load, I just always have a little quick calculator open here. So what we want to do is it's 90 kilonewtons, 90,000 newtons per meter length, and we want to divide that further by the width of the flange, 0.8, to give us kPa, or at least pascals in this case, 112,500. And we're going to define this as a pressure load, and we'll stick it on the whole of the top flange. Now Abaqus wants us to tell it which of the surfaces, top or bottom, brown or purple, we are going to use, just to let you see the purple surface. So there's purple at the bottom. We're obviously going to use the pressure on the brown surface, and it's positive onto the surface, so we'll just have the positive value, but you can confirm that by looking at the little arrows spots there. So I hope I've done everything I should have done. We'll define the job and run it. I'll just call this example shells and submit it. takes a while on the first, writing the input file on the first run, but it seems to have completed. Right, so obviously there's a lot of results to see. Reflected shape of the beam, maybe we should turn it again with the side view. So this is the left support. You can see stress concentrations happening there and there. But the deflected shape looks alright. Again, mesostress for a concrete structure is not of interest. We want to see something like principal stress, principal maximum in-plane principle would give us positive values. So this is the, or at least not only positive values, but the maximum values in terms of positive stresses are the tension stresses. So on the side view, we don't see anything of that nature really. Neither do we see it on top. You can see there's compressive stresses over there. We do S11. This is now the question, what are we looking at in terms of S11? What is the one direction? Now, if I just look at the output, we can see a continuous band along the flange edges like this, which basically means that the flange is bending in this transverse direction, and what we want to do is to just make sure what we're looking at. We can switch on wireframe on this little toolbar here. It won't show us anything now, and then we can plot the material orientations. Now that doesn't look very interesting because it's too dense, but typically you can go and maybe switch off the 3-axis. If we now go to that menu next to material options, and we can plot it in terms of screen size. It's better already, but it's still a bit big, so we'll make it smaller, the arrows. And it's often useful to plot this in the deformed shape. Right, so don't confuse the web here now with the directions, but let's just look at the end here. So we'll see in the web, as I've said, the local x-axis or one axis runs in the length of the beam, and on the flange it runs transverse. So if we're plotting S11 in the flange case, it's actually showing us the stresses in the transverse direction. And then this is quite confusing when you're looking at output of a model of this nature. So it's best to fix this. Now, one way to do it is to define a material orientation before you analyze. The easiest way in this case is just to align the whole beam with the global x-axis in the length direction. So I'm going to go back to the model, and we're going to redo the boundary conditions, and I'm going to rotate the whole instance. Go back to the model, we go to the instance of our T-beam. What we can do here is you'll see that the menu is here for translating and rotating things. So I'm going to rotate about the y-axis so the beam's length axis runs in the x direction. So when you click on the rotate tool, it says select the instances. We only got one instance. And I'm going to start rotating at 0, 0 and go up to the top of the flange there. That specifies our rotation axis. And we're going to go 90 degrees using the right hand rule. So we've flipped the whole structure now by 90 degrees, and it's pointing in the x direction at the moment. Just to show you what else you can do, we also know that according to our drawing, our coordinate system actually starts at the center of the support. So if it helps for some reason, we can translate the whole instance. So by going to the translate tool. Sorry, I always keep doing this. I have to press OK on the rotate thing, so let's just do it again, maybe for demonstration purposes as well. We select the whole instance and specify the start point, the end point of the rotation, 90 degrees, and just press OK, otherwise it forgets what you've done. You can translate it as well. Again, same instance. And again, now that's 0, 0, so we know if we click that as the start point of the vector, we want to go the negative x direction minus 0.1. Yeah, so the origin of our axis system is actually now at the center of that support. You say it's okay. Right, so now the boundary conditions obviously looks different. If we go to boundary condition 1, it's still fine, but boundary condition 2 is in the U1 direction, which is clearly wrong. So boundary condition 2 we want to support in the 3 direction. See that it's a bit unclear and it never gets bigger, but the screen basically shows there that we've now supported it again against rotation about X. The load is still fine. Let's reanalyze. Okay, so it's done. If I look at the results, again, this is where you change your display of the model. That's it's painted as solid. If you paint it as hidden, let's see if we can see the material orientation. So the one place you click it is over here where it says plot material orientations on the undeformed shape. Right, so as you can see, if we zoom in, this might not be clear. Let's go to the end of the beam. In the web direction, the blue vector is now pointing along the length of the beam, and so is the flange. So what we're going to get out, if we look at S11, is stresses in the direction of blue vector, the one axis. So if I do that, okay, so let's just go to undeformed. You'll see that now it looks more realistic. This is what we might be expecting. Right, so in the sag portion of the beam, we get compressive stresses over here, and then tension stresses over the top of that support. If we look at it side on in the YX plane or XY plane, Y pointing upwards, we'll see tension in the bottom, tension at the top at the support as expected. In the 2 direction, we'll also see this transverse bending across the width of the flange. So if we now go S22, it actually shows us a more, let's just now make sure that's the right thing we're looking at. No, might actually be, let's just do S1, 2, yeah, that's the shear stress, that's what we expected. And S22 looks a bit different from what it did before. I'm not actually sure why. But be it as it may, might have made a mistake earlier on. Let's just see again the material orientations. Definitely looking at the 2-axis direction in this direction. Right. Scaling on Abaqus has gone to a plot. Often it's a bit confusing because it looks like a very uniform scale it's actually showing you. There's not a large distribution of stress, but the reason is because the large concentrations of stress in this area basically overrides the whole rest of the model. If I switch off the web, it might actually help us to display those stresses a bit better in the top flange. You can do that by going to your create display group. Under element sets, so I've got a set here for flange, and I'm going to replace everything with that. And as you can see, it now looks like what we had before reanalyzing. Like, this is a neat trick to just get the contour plot to scale correctly depending on which part of the instance you're looking at. The reason it looks different from the analysis before is because the 2-axis in the previous analysis was actually pointing in a different direction. In this case now, the 2-axis is for the flange and the web, both pointing, they're both pointing in the same direction. So if we go all other elements again, we'll see that the stress concentrations at the end here overrides what we're actually looking at. Right, so now just the last thing we want to talk about again is what we're looking at in terms of the moments. The easiest way to visualize this is often, okay, if you plot the contour plot, you want to go to section forces, and we want to actually plot moments, section moments, and you'll see that SM2 gives us what we expect. It's a very small moment at the end of the flange where we haven't sort of the flange is cantilevering about the web, and then we've got these high concentrations in the two directions. So what we're actually looking at here is a moment about the one axis. So it's about the length of the beam, that axis. It's a moment in the two direction, if that makes sense. If we do the one moment, you'll see this is what we expect in terms of moments in the length of the beam. Concentrations over the support, and it changes in the length direction, but the moment now is about the two axis. Now to see what I mean by using this about the two axis, you can actually plot the symbol plot. Again, it's a lot of symbols, so what you can do is just again go to undeformed, and we change the settings by changing the size, making the size a bit smaller, and you can now see that it shows us an arrow that indicates the axis about which the moment occurs and not the direction of the moment. So the symbol plot basically shows us the axis of rotation of the moment, if you use the right hand rule, is based upon, not actually direction of the moment. If we go to section forces, so we go SF1, it's the forces in the length direction. You'll see that now the arrows do actually point in the length direction, because it shows the direction of the force vector. So you just need to know how to manipulate these things to get the correct answer out of Abaqus. As a final check, just as a comparison, I'll go to the Excel spreadsheet that I've created as a memo for this question. Let's give that a second to open. We're just going to compare deflections as a start to see whether we get similar results from the plane stress analysis and the shell element model. So I'm going to just see a side view of that. We can stay in the symbol plot, but we're just going to go to translations, and we're going to go in the two direction. Now you can see we get our biggest values over here. Maybe we should try and switch on the values and see if it gives us a label that makes sense. It doesn't. Okay, that's a bit tricky to see, but there we go. 1.024 times 10 to the minus 2 meters, about 10 millimeter deflection. Right, so I plotted various graphs in Abaqus that was expected. This was the shear stress through the depth of the beam. This was the axial stress through the depth. This was the actual moment, and the deflection. So this was actually the deflection predicted from the formula in the red book. But if we look at this tip deflection, just looking at what Excel gives us, it seems quite reasonable. We're at 10.4 millimeters in this plane stress strain analysis, and yeah, this gives us a pretty good correspondence in terms of Abaqus's value. Let's just do that. So 0.01024, and what I extracted from the plane stress model was 0.01046. So there's a very good correspondence in terms of deflection. There's various things we could obviously now compare. I'm not going to plot a path through the beam at the moment and extract shear stresses, etc. We could look at moments as an example to see what, or maybe stresses in the one direction, to see how that corresponds. So if we go to stress again, S11 should give us the stress at the top. So let's just go back to our 3D view, go to the contour. At the support here, we get a higher stress of about 12, what would this be? 10 to the 4, not very big. Oh, sorry, we're at moments now, not that stress. Apologies. We're looking at 16 megapascals. Okay, this is at the bottom there. We should probably query something at the top here. This one is the selected value, and we can pick an element over here somewhere. And it gives us 5.3 megapascals. In the stress plot, I get quite a higher stress, actually 18 megapascals. Now, these things are bound to differ, but the other reason it differs is depends on where you're actually plotting the stress in the shell element. You can change where Abaqus plots the stress in the shell element by going to result section points, and it basically comes down to these section points you define when you were doing the section definition. So you'll see that if you click on this, it gives you that you've got the negative face of your element and the positive face. So we want to be at the top. If we apply that, the stresses actually change. So this is quite an important feature. You have to remember that the shell element stress, or the shell element varies stress in terms of its thickness. So if you've got quite a thick shell element, it's reasonable to expect that there's quite a different stress on the bottom surface versus the top surface. So what I've selected here is to plot. If you look at the bottom again, oh sorry, it doesn't want to look. You have to pick it here. It's the negative surface apply. It's much lower. We're looking at only 16 megapascals. If we go to the top surface, we're looking here at something a bit higher. The red is now, again, we have to query it really. Otherwise it doesn't make sense. Yeah, you're looking at something like 20 megapascals at the top, which corresponds quite well, given that the analysis differ quite significantly in the type of elements used and the mesh sizing, etc. At the peak value here, we got about 19 megapascals, and Abaqus for the shell elements gives us about 20. So you'll see that obviously, again, deflections are quite accurate in terms of correspondence as for all finite elements, but the distribution of stress and forces really depends on the type of element you're using and where you're plotting the results. So we'll talk a bit more about this in a classroom discussion. That's where I'm going to end the video. I hope it was instructional and that you can learn something from it. Thank you very much.